Today I'd like to talk about why V negative and V positive in an op-amp are really equal. So when we first introduced the op-amp, we kind of had to lie to you a little bit just to make the derivation a little bit easier. And to refresh your memory, we derived V out equals minus R2 over R1 times V in. And the logic was a little bit faulty. And here is where it breaks down. While it is true that V out equals the open loop gain times the difference of V plus minus V minus, and it is true that V plus is equal to 0 volts, and it is true that V out equals AVOL times the negative of V minus. When we solve for V minus, we're turning V out into an input, and we're turning V minus into an output. Now, while this works mathematically, physically, it's meaningless. Now, the reason why it works is that some of this V out signal is fed back through R2, and so we're actually connecting a signal via voltage feedback to this V minus terminal. Now, while this is really simple, it doesn't allow us to derive an equation for when we want to calculate V out versus V in and take into account the effect of the open loop gain. So let's revisit our derivation of the inverting op-amp. We set up the currents because we're assuming Rin is infinity, I negative is 0, and I2 and I1 are equal to each other. And when we apply the voltage drop definitions, we get I1 and I2. But in this case, we're going to keep the Vx. We're not going to set it equal to 0 with the previous derivation. So again, V plus is 0, and we get V out equals minus the open loop gain times Vx. Well, now we substitute this in for, in fact, V out, because we're going to find out, we're trying to come up with an equation for Vx. In our previous derivation, Vx was set equal to 0. Let's see what happens now. So now we have I1 and I2. We set them equal to each other again, but instead of solving for V out, we're going to solve for Vx this time. And if you can go get the PowerPoints and go through this derivation a little bit on your own. So we get Vx equals Vn divided by R1 times the open loop gain divided by R2, 1 over R1 plus 1 over R2. So we can see now that as the open loop gain goes to infinity, all right, it drives out these components look like they're going to 0, and then 1 over infinity is 0, so the Vn over R1 goes to 0. So we get if V plus equals 0, then Vx equals V plus, and thus V minus equals V plus, because Vx was equal to 0. Now the thing is you can use that Vx to calculate really what would the Vx be if the open loop gain were 10 or 100 or 100,000 as opposed to infinity, which we can do in LTspice. So we have Vn, and this is an ideal behavioral voltage source. R out is equal to 0, and it's just the minus open loop gain times Vx. I've already set V plus equal to 0. You can look through these parameters, and I've even calculated what the output should be by hand and what Vx should be by hand. And when we run it, we get Vx equals 0.08 repeating 3. And when we calculate what it was using our equation, we get the same value. And we can see that V out measured and V out calculated are the same as well. Now the thing is this equation here, when open loop gain is 10, is not accurate. It's not a good estimate. And Vx is not equal to 0. Well, just as easily, We can set the open loop gain to 400,000. And now Vout equals almost 1. Vx is very close to 0. And Vout check and Vout are calculated to be the same. And you can even download this LTspice file and verify things for yourself.